Hi, I'm Milan Gandhi. We have developed a flight profile tool. This is the executable. We'll open it and it will take a couple of seconds to activate. So this is the tool application which is meant for the commercial pilots or the pilots undergoing training in flying academies or flying schools. So we'll look at how it is going to be beneficial for these pilots, and it can act as a simulator. So let's see the application parameters, input parameters. Here the flight plan, a pilot can enter the flight plan, then the aircraft which is going to fly, the code which is assigned by the IOC here, then the flight level at which he wants to test a particular path where based on the flight plan, and then there will be a cruise max at which speed he can test, and then the aircraft mass in kilograms is the takeoff weight, and you would be able to see what would be the aircraft mass when it's landing. So this parameters can pilot can keep on testing it with these parameters, and it would be very handy and beneficial for them. So this acts as a stimulator. So this particular tool is based on the BADA model, that is base of aircraft data. That's a movement model, and that's also called as a performance model, which is developed by Eurocontrol, and it's a total energy model. What it will what the output would be, it's like it would compute the jet aircraft's vertical profile and lateral profile. Three kinds of output file will be generated: Google Earth file, uh, Google Earth file, then the lateral file, and vertical file. Google Earth file will display the flight path, and lateral file which will be generated would be as similar as the Google Earth file with the detailed parameters in that, and the vertical profile will be from takeoff to landing, so with the detailed parameters. So what this particular application would be handy for the pilots to gauge the detailed parameters and test it around with the different parameters entered out here. For there could be different flight plans, there could be a different aircraft type, there could be a different flight levels they can test. They can test the speed with the cruise max when it's in the cruise, or different whatever the phase the aircraft is in. So via Mach number they can check that, and entering the Mach number and the aircraft mass. So three kinds of output will be generated in detail with the detailed parameters. Then this tool integrates the airplane movement model, atmosphere model, and the Earth model. Aircraft movement model has so-called technical characteristics as its weight, empty weight, maximum fuel weight, thrust of its engine, etc. And the performance data such as stall speeds in different configuration, the speed of the cruise, the flight capacity that is necessary to take into account to carry out the calculations. Then the atmospheric model, that is ISA model, makes it possible to overcome the location of the aircraft by the standard temperatures, pressures, and density as a function of altitude. Then the Earth model is necessary for both atmospheric and special, that is out of atmosphere calculations. There are three types of forces acting on the aircraft: the gravitational force, the propulsive force, and aerodynamic forces. The gravitational force is applied to the center of gravity of the aircraft. Propulsive force pulls the aircraft forward, and aerodynamic forces are lift, drag, and lateral force by the generated by the drift. The vertical profile is the file which will be generated, where it's a flight profile that corresponds to the altitude and speeds reached as a function of time and distance traveled. A profile follows a sequence during which the typical configuration of the airplane will evolve. The typical sequence of the flight envelope is takeoff, initial climb, cruise, descent, approach, and landing. So the different configurations for takeoff starts with the takeoff, that will be lift and track configuration with a thrust. That's a thrust is the force which moves the aircraft through the air. This is generated by the engines of the aircraft. The thrust for the takeoff would be maximum climb thrust settings. Then the initial climb will have the configuration of lift and drag configuration and maximum climb thrust settings. The climb phase will have clean aircraft configuration with maximum climb thrust settings. The cruise phase will have a clean aircraft configuration with the cruise thrust settings. Then the descent phase will have the high and low thrust settings, and the approach will have descent will also have the clean aircraft configuration, and the approach will have an approach aircraft configuration with the approach thrust settings. Then the landing will have the landing aircraft configuration with the landing thrust settings. So this is basically a total energy model and based on BADA. So what we do is we'll just enter the flight plan. This is the flight path, the flight proposed flight in compliance with the ATC, that is air traffic control. Then so the flight plan which we have entered here is this is the ADP, the departure airport, and the ED and we got ADS, that is the arrival airport. And this is from CYMX, that is the Montreal Mirabel Airport, runway 06, and it will land at EDF, that is the Frankfurt Main Airport with around runway 25C. And these are the waypoints: Tamco, Meteor, Dyson, and it goes to Kola, Rollis, and then it will land at the Frankfurt Main Airport. So this is the flight plan, and this is we're going to use A310, Airbus 310 as the aircraft. These are the regulators, International Aviation Regulators. That's the International Civil Aviation Organization which assigns the code. And then the flight level will test this particular flight level of 390, that is 39,000 feet, which is going to be cruising at 39,000 feet. And so we'll have a look into that also. And then the cruise Mach will take a speed of 0.83. So that's the speed we'll check at the 39,000 feet. And the aircraft mass is say 120,000 kilograms. So this is the parameters entered for this particular demo, and this can be changed. Whatever the parameters we enter can be changed. But in a battle model, there are threshold values to be put, like Airbus 310 cannot fly over 39,000 feet, or the cruise Mach cannot be over 0.83. So and the aircraft mass and so on and so forth. So the thresholds has to be taken into consideration, and the performance will be of the aircraft can be gauged. So when we submit this particular, I'll click on the submit button. You will have 3 files generated, and that would be in the folder from where we've started this application. That will be result files folder, which will contain 3 files, and we'll have a detailed look into that. So this is the way we'll start the application, and we'll just have a look at the details. And submit button we click. In the background there will be a program will be running. This is the program running in the background, and files created. Okay, it's creating the files. Okay, done. So the file folder which I was mentioning about is already generated here, and which would contain all the three files which I said would be there. This is the Google Earth file, and this is the Montreal. This is the lateral profile from Mirabel Airport to Frankfurt, and this is the vertical profile. So vertical profile for takeoff to landing, we'll check the altitude, speed and stuff, all the other parameters. And we need to we'll click first. We just see here it has given the flight plan, flight path length. This is the total length of the of this particular flight plan. It would fly 3,204 Nottingham miles. 1 Nottingham miles is called 1.5 miles. So this is the total length of this particular flight will fly. So this is done, and we'll go and check out the this is the Google Earth file. We'll click open it. You need to install Google Earth Pro to visualize this. So this is the way it will appear, and here we will see the detailed of this particular flight path, flight plan you can say. So this is generated. So we have come here. So this is for us. Let me open the same scenario is presented in this Excel file. This is a lateral file. So what we are going to see in the Google Earth file is basically in Excel file also with detailed parameters. How many with the detailed parameters, that will be very explanatory for the pilots to understand the way this particular journey is taken about. So this is the file. Yeah, so these are different parameters in this, and now we'll first go to the Google Earth file. We'll what we'll do is just go to file and get back to where exactly we want to start. We will go to the takeoff airport. Yeah, so Montreal International Mirabel runway 06 is here. Then if you look at the flight plan, you can see Tamco, Meteor, Dyson, and so on and so forth. So first let's look at Tamco, Meteor, Dyson. Where is it? It's here. Tamco, Meteor, Dyson, so on and so forth. Now this is the takeoff point. Now we have entered 39,000 feet as the we want to check the 39,000 feet at the cruise level. The cruise Mach would be 0.8. So based on that, we just have a look here. So when it enters the cruise phase, the yellow highlighted marks is where the cruise phase starts. It's basically from Dyson, just before Dyson, this particular point, it starts into the cruise phase. It enters the 39,000 feet. So from here, from the takeoff to the initial climb, and then the cruise phase at 39,000 feet at 0.83 Mach is flying. So and it covers all the flight flight path. So we've seen this river. Then we'll just go ahead, and we'll see all the waypoints. These are the waypoints: Cherokee, Lemmy, Lonsi. Here you can see that these are the parents, right? There are Lonsi, Renzo, Netki, and so forth till Kola Rollis. We'll see, and then the landing airport. So this is the way it's going flying. This is at present flying at 39,000 feet, and with a cruise map of 0.8 what we enter, and it comes here. Sorry, we'll just go back and revert. Skips, yes. So this is the way the Google Earth displays the whole flight path, and so we were here. So this is the cruise phase which we are looking at, and it covers all the waypoints: Netki, Renzo, Belfast, and so forth. We'll go to a point of landing now. This is where it's going to be landing. We just got to put a pin that particular so here we'll get it. We got to just pin it properly to get the landing airport. Yeah, we've come. So here it is going to be the ground run. So it's landing here. Ground run. Let me check this particular where's the Mirabel. I mean, it is the Frankfurt main runway. That is 25C. This is the where it lands. So this is the way this particular Google Earth will display the Frankfurt main runway 25C. So it has reached here. Here the basically a yellow highlighted area which is still there. Here the flight is in the cruise phase, and then it starts descending and approach and landing, and then the ground run to the main Frankfurt airport, main Frankfurt airport. So Collis, Rollis, and all. So this is the way this particular Google Earth file will show us the with the turn points and latitude, longitude. Will come here later on. This is the way it the latitude and longitude. Will go to Jason to see that. So we'll just revert it back so it comes back to normal. Yes. So we will come back to this particular takeoff point, and here you can see first let me revert it again so we could get from the takeoff point. We'll take so here what we display here is the this is the takeoff point, and if you look at a Dyson, you can check here. These are the longitude 70. This is the longitude and this is the latitude. You can check that also with the turn point degrees when the flight is navigating through the path. So this is one point. We'll have a look. Come later also. We can have a check on this particular. There are particular longitude, latitude degrees we need to see. So this is there. Now this is the detailed description of the what basically is the lateral profile all about. So this is the first is the elapsed time seconds. How many seconds it took to fly from the takeoff to landing is here. We'll just see how much seconds. It's in seconds. So it says how many seconds is here. It's landing at Frankfurt, right? So it's 26,417.7 seconds. That comes to 440 minutes, and 440 minutes, that's 7 hours 20 minutes. And this is the duration of the flight from Montreal Mirabel Airport to Frankfurt Main Airport. The duration is 7 hours 20 minutes. That's displayed here. Then generated here. These are the waypoints what we saw from Mount Maribel. If you go down, just check. These are the waypoints we entered. Ground run, so and so. So yeah, it's several lot. Here you can just check in the here. This is the one, this waypoint, and this can be also displayed in the Google Earth. This one, this is Java, right? And same you can see Dyson and stuff like that. So this is the way it's shown the waypoints, and if you then the longitude will be there. Yeah, this is the longitude column. This is the latitude column. So let's have an example of Dyson, which is at this is at 1194 seconds. So we'll go to Dyson 1194. Yeah. So let's look at the longitude is 72 degrees and the latitude is 46 degrees. So if you have a look here in the Google Earth, we just you can check here what's the longitude and latitude. So when I said this Dyson, this is it. If you can check look at it, so it's got 71 degrees right now, so it's not in the precise point. 72 is supposed to what we saw, and the 46 you can see the latitude. 72 here it was, and 46 here. So precisely if you look at this particular Excel file, the same thing, 72 degrees and 46 degrees for longitude and latitude. So this is the Google way. The Google Earth helps us to check, cross verify with this particular Excel file. And the cruise phase, we'll just come back to that later. This is one done. Now we'll look at the latitude, meter, altitude. So altitude is basically the flight level to meter conversion, and flight level to feet. So we'll look into the what the altitude is basically in feet. So we can check this with what altitude we want. It was 39,000 what we entered here. So we will check that 39,000, and we'll check the cruise map also. Okay, so the first thing we'll do is go to this altitude of we want to check the altitude at 23,000 seconds, 23,000 seconds and to 639. So here we are 23,600. Yeah. So 23,639 seconds we will be looking at. 29:36. So yeah, we're just going to precise this particular thing. 23:39. So a little bit over here. This is with precision. So we're just taking a bit. So 23,639. If you look at that, this particular row, this is where the altitude we are talking about. So this is almost 39,000 feet, 38,978.82, 39,000 feet. Where in the cruise, with a cruise of 0.83. So which we'll see, the cruise will, the Mac will see in the other file, the vertical profile. So this is 39,000 feet reach. Okay, it reached at 23,639 seconds. That is approximation of 394 minutes. Okay, and so if you look at this particular Google Earth, one more thing can be derived at this is at this yellow highlighted. When it enters the cruise phase, it's after say 18 minutes of the from the takeoff. It will go to takeoff, initial climb, and then the cruise phase. So after 18 minutes, it's just entered the cruise phase, and this lasts till the yellow highlighted. Where is it? Yeah. So it will last till this particular yellow highlighted here. So yeah, Europe will be where the the cruise phase ends, and then the descent starts with then the approach and the landing will be done, and then the touchdown is there. So this basically covers almost 6 hours 15 minutes in the total flight time. So out of 7 hours and 20 minutes of a flight, 6 hours and 15 minutes is in the cruise phase, and that is very economical for an airline, and that's the reason the cruise phase is very important, because the fuel efficiency increases in this cruise phase. So that's another topic altogether. So this is the way it is, and then we look at which one? The altitude is done, and altitude in feet is done. Delta distance Nottingham miles. What's a Nottingham mile is equal to 1.15 miles, and delta means it's a pressure divided by the sea level pressure, converting them into meters and into knot. This is meters, and this could be for Nottingham miles. And then we have the cumulative distance in Nottingham miles. That is calculated distance for the position reports on the ground. So it's got an algorithm which is distance underscore cosine, and which is applied, and the formula is cumulative distance under the bracket the positions, which will give us the in Nottingham miles. So this is the cumulative distance for the ground reports generated. Then this is the course angle degree. The course of the aircraft is the cardinal direction in which the aircraft is to be steered. Heading is the compass direction in which the aircraft nose is pointed. So this is what this lateral profile file generated, along with the this is as similar as the Google Earth file we saw. We just go back, maybe we can come back here later. So this is the way this particular lateral profile can be handed to the pilots, and then we'll after this we'll have a look at this. This is done. Lateral profile is done. Now let's go to the I want to change the Montreal cancel. Let's see. rate will come there. And now this is done. So we'll go to another file, that is a vertical. Don't say, we'll go to the vertical profile. This is the vertical profile from takeoff to landing, and the speeds and altitudes will check out here. So this is generated for this particular flight plan, the flight path. So this columns, we will just go through the columns out here. The one is the this ellipse time seconds, in how many seconds you can check again. Down, how much is there, what we saw in the earlier file, Excel file, the same 26,416.7 is the total time taken. That comes to 440 minutes, that is 7 hours 20 minutes. So this file also generates the same sort of what we saw in the latter file. This is altitude in mean sea level meters, and this is the altitude in mean sea level feet. This is what with the cruise map, what would be the cruise phase we are talking. The cruise phase we entered here, we can check here also. So this is what 39,000 will check, and then what is the cruise map will check that also. So this is that particular. Let us go to the another column. This column, what we saw here, altitude speed, which we saw in the previous file also, the lateral prior. We'll come back to that later. This is the true airspeed meters. Now true airspeed meters is something basically it's calculated. This is in meters, true airspeed meters seconds, and true airspeed knots. True airspeed knots is the way it's been normally pilots would calculate it. This is the 2% increase of the indicated airspeed. So we'll take an example, and so we can have a better understanding of this. Suppose the indicated airspeed is 170 knots. So we go to the flight level at 8,500. Let's go to the how many seconds is that? 2 so we'll go to 241 seconds. So this is 241. Yeah. So this example will show us basically what the speeds are. So the true airspeed is we are saying that we are at 8,500 8,500 feet the altitude, and then we'll see the 2% increase, and here the indicated airspeed is basically 117 knots. So it should be 2% increase in this particular, for the true airspeed increases 2% of this particular IAS speed, that which is 170 knots. Now based on that we'll have a particular increase here. This is true airspeed which is giving 223.73. This is actually incorrect. It should give, this is calibrated airspeed. This gives the correct answer, because this is incorrect. If you calculate 170 knots based on 170 knots flying at 8,500 feet with 2% increase in the IAC speed, the true airspeed should be it's showing 223.73. If you calculate it, it is wrong. It's corrected by the calibrated airspeed, which is 197. So calibrated airspeed, what it does is it's a correction for the instrumental and the position errors. So it is corrected here. The true speed is corrected here. So this is the example we saw how it is done. So then we'll look at the Mach. Now we'll look at a Mach. This is the Mach column, Mach speed. So what we entered here was 0.83. We wanted the cruise, it should at flight level 39,000 feet, it should be 0.83. So we go to this and we'll check when it starts. We want to see when it this particular speed is achieved, and it will start at it will start at there is a rate of climb. Okay, so we just go down. A little bit more. Yeah, so this is another column called the rate of climb and descent per descent feet, which is this column. So what it does is basically this is the variometer, which pilots will have an instrument called variometer, which will showcase them the rate of climb and descent. So we'll go back to when it starts the rate of climb. So right now we're looking at this particular because we want to see the speed. We want to check the speed, which the 0.83 when it starts. So when it's reached at this level, it starts stopping. The rate of climb is it's entering the cruise phase. Now it is entering the cruise phase. We want to check when it starts 0.83. So here we'll see. Yeah, we're coming nearer. You can check this. 0.1 we have come. And in the cruise the Mach number, yeah, so 8.829. This is just go a little bit. So it's entered the cruise phase, but the maximum of 0.83 is achieved at what point we'll see. Yeah, 0.82. Okay, we just got to go to a little bit more. We want to see the achieved speed of 0.83 to be precise. We're just going to the precision here. So it's going. So we just go down. It's not reached. No, still not. So maximum is 0.93, 0.292929, and it's 1 somewhere. Yeah. So maximum is achieved here. So it is going into the cruise phase, and let's go to 23,000. So you see the rate of climb, this is becoming a blank, and we see this particular speed which will end here now. Yeah, so here is the maximum which we have reached, 0.829536, that's 0.83 Mach, that's the speed. And once it is reached here, the descent phase starts. So the rate of climb and descent via the variometer instrument will showcase this particular thing. So the cruise phase has ended, the descent phase has started. So so this is the way it flies, and then we'll have then we'll look at the rate of climb when it starts, basically the rate of climb, this particular column we were talking about. So rate of climb we were talking about, it starts with the 33 seconds after takeoff. So this is where it starts, this climb starts. That is 34 seconds, and then it goes till it will go to 114 seconds. So this is where again we'll go down 1 1 yeah. So this is going here, you can check here till 1 yeah. So this is where the rate of climb till it goes. Rate of climb is there, and then here it starts. Sorry, it starts and it will end here. So 33 started and will go to 1114 seconds. Yeah, you can see this. So the rate of climb means the rate of climb is completed when it starts at 33 seconds. At 144 seconds the rate of climb is completed. So it and then the cruise phase starts, so it becomes 0. And then when it enters the when the cruise phase ends at 23,639 seconds, the descent will start. So just precisely we'll go. So yeah, so here it starts again. I meant to say this was the beginning. Sorry, we just got too far. We just got to go to 23,000. We are nowhere here, at least. Yeah. 24,000 it is. So yeah. So this is where the descent phase starts. So this particular variometer can give this particular information to the pilot. Then the next column is the flights flown. It's distance flown in Nottingham miles. So what is the total distance? What we saw here is 3,226.573 Nottingham miles. When we had clicked on the submit button, we had got the same thing, 3,000. This is 3,204. Now this particular is different. 0.2 to Nottingham miles is the difference between what it is showing here. It's showing 3,226. The reason being, it's a ground run is taken into consideration here. So that 0.22 Nottingham miles is added to this. And the next column will see how much, this is what we saw on the other interface, the flight length path. It says is 3204 is the Nottingham miles to fly. So when we see this particular thing here generated, that is 3204. So the time generated here is precise. This was the this is distance to fly when it started to take off. This is the distance flown when it ended. So that 0.22 Nottingham miles were added. So it became 3226 Nottingham. Then we have got aircraft mass. Aircraft mass, it's basically Newton's weight equation, where the formula is mass into gravitational force. When we took off, we flew at when the takeoff weight was 1,20,000. But when we look at when the flight ends, when it lands, what is the weight? 1,20,000 was the takeoff weight. We'll go in the bottom. So when the flight lands, what is the weight? So it's 91,422. It was 1,20,000 when it took off, and now it is, when it lands, it's 91,425. So there is a difference. There are a lot of factors to consider. Emission of gases are there, and the gravitational force acts on this particular mass, so the mass is reduced. So then we'll have the angle between. The other column is this one, is the flight path angle degrees. So what is flight path angle degrees? Is the angle between the horizontal and the tangent to the flight at a point. So to see this particular, how it is calculated, we'll go to 523 seconds. That's almost 8 minutes into the flight. So 523 seconds will go. So yeah, here it is, 523 seconds, and we are looking at here we'll see, this is the column of what we are going to calculate. So how it is calculated is at 8 minutes to the takeoff. After the takeoff, the what is the angle degree? What is the flight path angle degree? So it is 4.78. It shows. How it is calculated is the rate of climb divided by velocity. Suppose the rate of climb is 5 meters per second, and the velocity is 60 meters per second. So when you divide this, you'll get this particular angle of 4.78. This is so the flight path angle degrees are calculated like this. Then there is a thrust column. The thrust is basically Newton's third law. Every action, there is equal and opposite reaction, and this is a powerful force that is responsible for moving the airplane forward. So thrust is there, and then we have this is the thrust. Then the drag we have. It is basically thrust is generated by the engines of the aircraft. Then we will have is the drag. The drag is a force acting upon opposite to the directions of the movement of aircraft. So it's a second law of Newton's second law. Drag is equal to gravitational force, thus producing net force of 0. So this is and then we have the lift. Lift is an aerodynamic force that is perpendicular in direction in order for an aircraft to rise into the air. So force must be created that equals or exceeds the force in gravity. This force is called the lift. This is also Newton's third law. If you go to 33 seconds, so 33 seconds, you can see this this lift has gone. So this lift was still 33 seconds after the takeoff, and This is the lift part of it, and then we'll have a look at the load factor. Load factor is we calculate it's calculated by lift divided by weight, and units are referred to as G. Here you can see. So load factor is G. G is the units it is referred as. So if the load factor is 1 or -1 or something, here what we saw 1, or then it is because of the it's because of the result of the maneuvers or the gust winds. And if the load factor is 0, when it comes to 33 seconds, it will become 0 when it starts the initial climb phase. So it's 0 because it's called as a wait list, and this is the way the load factor can be understood. So these are the detailed parameters of the vertical profile. We saw the horizontal profile, then we saw the Google Earth file. This is where we started off, and this could be a very handy tool for the pilots to gauge the different parameters. And thanks for watching this.